Chapter 1, Why Verifiable Rewards Matter. Start with the central shift. Language models became very fluent before they became reliably correct. Given a prompt, the model writes an answer, and the answer may look polished even when it is wrong. That is the uncomfortable part. Fluency is not the same thing as correctness. In open-ended conversation, we often judge helpfulness, tone, or style. But in math, code, database queries, structured extraction, and many scientific tasks, the output can often be checked by an external procedure. The important difference on the screen is between an answer that only sounds good and an answer that checks out. Reinforcement learning with verifiable rewards uses that second property. A verifier evaluates the completion and turns correctness into a reward signal. So the training target is not style alone. It is whether the model can produce outputs that survive an explicit check. Chapter 2, Problem 1, SFT is target-based. Supervised fine-tuning is powerful, and it is usually the first tool we reach for. But notice what its loss function says. It treats one demonstrated output, y star, as the answer, then increases the probability of that exact sequence. That is appropriate when the target is truly unique. But many reasoning and programming tasks are set valued. A Python string can be reversed with slicing, with a for loop, or with the reversed function. The surface forms differ, but the behavior is correct in all three cases. Ordinary target-based training privileges the single demonstration and gives less credit to other correct paths. This is not because SFT is bad. It is because the supervision format is narrow. RLVR changes the question from did you match my demonstration to did your output pass the verifier. Chapter 3, Problem 2, Preference is not correctness. RLHF is useful when quality is subjective. Human preference can capture helpfulness, tone, elegance, harmlessness, and clarity. Those are real goals, and a deterministic checker cannot fully replace them. But for math, code, and structured outputs, the central question is often more objective. Does the answer equal the ground truth? Does the code pass the tests? Does the JSON satisfy the schema? Did the proof step preserve equivalence? In those cases, preference is a proxy for something we can sometimes measure directly. A human may prefer a confident explanation, but a verifier can reject it if the final answer is wrong. RLVR uses the external verifier as the direct correctness signal when such a verifier exists. The key phrase is when it exists, because not every valuable behavior is mechanically checkable. Chapter 4, Formal RLVR Setup. Now we can state the formal setup. A prompt X is drawn from the data distribution. The language model is treated as a stochastic policy, pi theta, which samples a completion Y. The verifier V receives both X and Y and returns a scalar reward, often 0 or 1, although it can also be a graded score. The objective J of theta is the expected verifier reward over prompts and sampled completions. Training adjusts theta so that completions with higher verifier reward become more likely. This is why the verifier is central. It defines what the expectation is measuring. The verifier can be a symbolic math checker, a unit test suite, a compiler, a schema validator, or any external procedure that maps an output to a reliable score. Chapter 5, Autoregressive Policy. The policy is autoregressive. The answer is not produced all at once. It is generated as a sequence of token choices. First the model chooses one token, then it conditions on the prompt plus that token, then it chooses the next one, and so on. The probability of the whole completion is the product of all those conditional probabilities. In log space, that product becomes a sum. This matters because RLVR usually receives a reward for the whole completion, but the model parameters control token probabilities. So the learning problem becomes token-level probability shaping from a sequence-level signal. A correct final answer tells us the trajectory was useful, but it does not automatically tell us which token choices were essential and which were accidental. Chapter 6, Policy Gradient Intuition. The policy gradient intuition is simple, but very important. If completion A receives high reward, the update increases its log probability. If completion B receives low reward, the update decreases its relative probability. The gradient is reward multiplied by the gradient of log probability, so reward acts like a weight on the sampled trajectory. The baseline B is a variance reduction device. It asks whether the sample was better or worse than expected for this situation. If a reward of 1 is common, then reward 1 is not very informative. If reward 1 is rare for a difficult prompt, it is a strong signal. So the model is not merely reacting to raw reward. It is reacting to advantage over a baseline, which makes learning more stable. Chapter 7, Credit Assignment Problem. Credit assignment is the first major difficulty. In this example, the first step, 7 times 8 equals 56, is correct. But a later arithmetic step is wrong, and the final answer fails the verifier. With outcome-only reward, the verifier only sees the end result. It returns 0, and that 0 is broadcast backward across the whole sequence. The update does not know that the early multiplication was good and the later addition was the actual problem. This creates a sparse and sometimes crude learning signal. Outcome rewards are attractive because they are easy to compute, but they can be inefficient. They say whether the whole answer worked, not exactly where the reasoning succeeded or failed. Chapter 8, Process Rewards. Process rewards address credit assignment by scoring intermediate steps. Instead of waiting until the final answer, the verifier or reward model can give feedback for expanding, simplifying, isolating, and producing the answer. This makes the reward signal denser and the attribution more precise. A correct algebraic transformation can be reinforced even if a later step fails. The trade-off is cost and reliability. A process reward requires a checker or labeler that can evaluate reasoning steps, not only the final output. That is much harder than checking a final number or running unit tests. In practice, process rewards can be powerful, but they introduce a second verification problem: who verifies the verifier at each step? Chapter 9, Group Sampling and Advantages. Group sampling reduces noise by comparing completions that came from the same prompt. The policy does not generate only one answer. It generates a group of possible completions. Each completion receives a verifier reward, and then the rewards are normalized within the group to form advantages. This converts raw reward into a relative success signal. The question becomes, which completion was unusually good compared with the other completions sampled for this same prompt? That comparison is useful because prompts vary in difficulty. A reward of 1 on an easy prompt may be ordinary, but a reward of 1 on a hard prompt may be exceptional. Group relative advantage keeps the learning signal local to the prompt. Chapter 10, PPO/GRPO Stability. PPO and GRPO are used to keep policy optimization stable. Without a constraint, reinforcement learning can push too hard toward whatever currently receives reward, and the model can drift away from useful language behavior. We start with the old policy. A proposed update tries to move probability toward high advantage completions. But if the probability ratio ρ moves too far from 1, clipping limits the gain. A KL penalty can also discourage the new policy from moving too far from a reference policy. The accepted update is a clip-safe update, not an unlimited jump. GRPO keeps the group relative advantage idea and avoids training a separate value model, which reduces memory and training complexity. Chapter 11, DeepSeek R1 and Modern RLVR. Modern RLVR scaled this same loop. DeepSeek Math introduced GRPO for mathematical reasoning, and DeepSeek R1 showed how reinforcement learning on verifiable tasks can elicit behaviors like checking, reflection, and retrying. The important claim is not magic. The important claim is incentive design. If the training environment repeatedly rewards correct math, working code, and STEM-style answers that survive verification, the policy learns to allocate more probability to patterns that lead there. We should be careful not to overclaim. The reward does not directly open the model and insert reasoning. It changes the distribution of completions. But at scale, that distributional pressure can make structured reasoning behaviors appear much more often. Chapter 12, Reasoning Improvement or Reallocation. There is an active research debate about what RLVR changes. Hypothesis A says RLVR improves reasoning quality. The model becomes better at constructing valid chains of thought. Hypothesis B says RLVR mainly reallocates probability toward good trajectories that already existed in the base model but were not sampled often enough. This distinction matters for evaluation. Pass at K checks whether any sampled final answer is correct, so it can reward lucky final answers even when the reasoning path is poor. COT pass at K asks whether the reasoning path is also correct, not merely the final number. That makes the evaluation stricter. It asks whether RLVR is improving reasoning, or mostly improving selection among existing reasoning attempts. Chapter 13, Verifier Failure Modes. The verifier is the objective, and that creates failure modes. A brittle string checker may reject 1/2 even though it is mathematically equal to 0.5. A weak test suite may approve code that passes visible tests but fails hidden edge cases. A schema validator may accept JSON that is syntactically valid but semantically inconsistent. These are not minor implementation details. In reinforcement learning, the model optimizes the reward it receives. If the verifier is incomplete, the model can learn to exploit that incompleteness. If the verifier is too strict, it can reject valid diversity. If it is too weak, it can reward shortcuts. RLVR is only as good as the verifier it optimizes. Chapter 14, End-to-End RLVR Training Loop. Now the whole RLVR loop is visible. First, sample prompts from the training distribution. Second, generate a group of completions from the current policy. Third, run the verifier and assign rewards. Fourth, normalize rewards into advantages, often within each prompt group. Fifth, update the policy with a clipped and regularized objective so the model changes gradually rather than destructively. Then repeat the loop. Over many iterations, the policy distribution shifts toward completions that are more likely to pass the verifier. This is the central mechanism: sample, check, compare, update, and repeat. The model is not given a single correct transcript. It explores candidate outputs and receives an external correctness signal. Chapter 15, Closing Takeaway. The final takeaway is precise. RLVR does not make a model learn truth directly. It makes the model learn the behavior that the verifier rewards. When the verifier captures real correctness, that can be a powerful route to better math, code, and structured reasoning. It also handles the set-valued nature of many tasks better than a single demonstration, because many different correct outputs can receive reward. But when the verifier is brittle, incomplete, or misaligned, the model will optimize that weakness too. That is why RLVR is both exciting and dangerous. The learning signal is objective only relative to the checker. In RLVR, verifier design is objective design.